All right. Good to see everyone, and welcome to lecture 11. So today we're going to talk about measurement and timing in the context of performance engineering. But first I want to make a quick administrative announcement. If you've looked at the calendar or paid attention to some of the recent announcements, we have a quiz coming up. The first quiz in the class is going to be a week from the next session, so a week from this Thursday. But this is the last regular lecture by me and Charles before then, so I wanted to mention it. We have a guest lecture coming up on Thursday, which should be really interesting, but I'm not necessarily expecting her to make announcements on our behalf. And then we'll have no class next Tuesday. I think it's like a Monday schedule after the holiday next weekend. And then we have the quiz the following Thursday. So one time critical thing on this, you have one more chance. Right now is your last chance to fill out the proctoring poll that we sent out, or also I think everybody to whom this is relevant has, but if you're someone who needs, who's in a faraway time zone, definitely let us know ASAP. We're going to decide on all of the policy issues related to the quiz immediately after this. So please fill that out right now. And I think Helen has just posted a link in the Slack if you still haven't done that. Again, the quiz is going to be, I think this was mentioned before, but the quiz is going to be in class. We're doing it on Gradescope. This is new to us. I think a non-trivial number of you have probably already done it before. There are two example quizzes that we posted from the last 2 years. We posted those in their original PDF form, and then we've also adapted one of them to the Gradescope format so you can try out what that might be like if it's unfamiliar. I encourage you to go through that to make sure that you're comfortable with the tools before we get to doing the quiz. We're going to, just one caveat with that, the question formats in previous years were developed, under the assumption that they were going to be given out as PDFs. So some of them fit a little bit oddly into Gradescope. Obviously, the questions we developed this year, we're going to try to make sure they're fairly straightforward to answer in the Gradescope format, but that should still be a rough indication of what the experience will be like. I think there's going to be a quiz review in section this Friday, I believe. And then, as we mentioned before, the quiz is going to be open book, but with no human interactions. You're not allowed to talk to anybody in the class or otherwise. All right. So with that, let's get started talking about how to measure and time performance of programs. Okay, so the basic workflow that we introduced way back in lecture 1, in which you've been practicing in all the projects you've done so far, and will be the focus of most of what you do in the rest of the semester, looks something like this. So you can think of the performance engineering process as a loop where we think for a while, we have some problem we're working on, we want to make a fast program that solves that problem. We think for a while, based on ideas we've come up with in that thinking process, we write or modify our code. And then we run that code potentially a bunch of different times or in different ways to measure and test different implementations. Based on what we see testing those different implementations, we come back to the top of the loop and think again about whether or how we might further improve performance and repeat this whole process. So, thinking about this process and about all your experiences in this class and in other contexts where maybe you've tried to optimize performance so far, why should we care about measurement? Why do you think measurement is an important part of this process? Or what are some of the ways we might use measurements? Why are they interesting? Anybody have ideas they want to shout out on Slack? As performance engineers, why do we care about measuring things? Get to know the effect of optimizations. If our program requires a certain benchmark, I think maybe you mean like we need to measure the thing that we're trying to optimize. And yeah, another good observation, it gives context on where optimizations might have the most effect. Yeah, these are all good ideas. Yeah, we might want to be understanding the trade-off between optimizations, how much benefit they give us, and the added complexity. Another interesting thought is maybe we want to check if our program actually follows and matches theoretical predictions. We'll see an example of this in a second. Theory is really useful, but simple models don't always give us a complete picture of what real performance winds up turning out to be. Yeah, so that's great. All right, so let's make the process a little more concrete and precise. So we can think of the performance engineering workflow as a procedure something like this. So if we have some program A, the program that we're starting with, we start out with that initial program, and then generally the first thing we do is, this is the thinking and the coding step, we make some change to that program A that we hope will make it faster. And that's going to give us a new program, call it A prime. Then we can measure the performance of A prime. If it's better, so if A prime beats A by whatever metrics we've set up, and we keep A prime as our new program. If not, maybe we stick with the previous program that we had. And if whatever program, whatever best program we have at this point is still not fast enough, we can go back to step 2 and repeat this process. So the vast majority of this class is focused on step 2 here. So on all the different ways that we can make a program faster. That includes things like Bentley rules, all the different compiler optimizations we talked about, parallelism, vectorization, and also the memory cache and other optimizations that we'll cover in a couple of weeks. That's what all that stuff is all about. But if you, sorry, getting my Zoom interface out of the way. But if you look at this loop, you'll notice that measurement actually appears twice. And it's kind of easy to take it for granted, but I'd argue it's every bit as important as the optimizations that we make. So if we can't clearly measure the performance that we care about, we have no way of knowing if we're making progress. And also it's important to realize that performance isn't really a single quantity. There might be different metrics we care about in different situations. So we need to decide, what is it that we even want to measure? And how do we want to turn that into a quantitative metric that we use to assess how good our different programs are? And importantly, we don't just need to measure, but we also need to be able to compare measurements. So sometimes we make changes that are so obviously better, we make things orders of magnitude faster, that it's really trivial to see. But often, as you've probably seen in the projects in particular, where you spend a lot of time building up optimizations on one problem, big wins actually often come not from one single trick or change, but from accumulating lots of smaller improvements that add up. And you can't do that if you can't reliably measure, reliably and precisely enough to clearly identify those small changes. Okay, so what and how well we measure matters. Now, let's think for a second about how we can measure performance and what issues might come up. I mean, at some level, we've glossed over this for most of the semester so far, so how hard could this be? Well, let's look quickly at an example. So let's say that we wanted to measure the time taken for a simple sorting routine. So let's say we have a basic comparison sort routine. We're calling it MySort here, that sorts an array of doubles. And this is based on a study done a while back by one of Professor Leiserson's former students. Okay, so what do we have here? So first, we're importing a library routine, importing a library that includes the clock get time routine that we're going to use for measuring our performance. We have some simple declarations for the sorting routine that we're going to be running. That's just some external code that we've written somewhere else. We also have a little helper routine for filling an array with random numbers. That's going to give us the test data that we're going to run our sorting routine on. And we have a little bit of setup code, in particular, the clock get time timer routine that we're using returns time in these time spec structs. So we've declared a few of those. And then the basic experiment we're running is that we're going to loop over arrays of increasing length. So we're starting with an array length n of some minimum value, and here we're starting with a minimum value of 1. And then up to a maximum value of, in this case, 4 million. We're going to incrementally run by some linearly sized steps. So we're going to increase the array in steps of size 20,000, making it 20,000 elements longer each time around this loop. Each time we go around the loop, we're going to fill in n random variables into the array. We're going to measure the time before we start sorting. That's going to give us a start time here. Then we actually run the sorting routine, the thing that we're interested in benchmarking. Then we measure the time after sorting, and then we just compute the difference. We compute and print out the elapsed time. There's a little bit of extra complexity just because these time structs are broken down into a few subcomponents, but we're basically just subtracting the two times from each other. All right. Pretty straightforward. Now let's think for a second about what we expect to see. So here I'm going to be plotting the runtime as a function, so the running time of the sort routine between those two timer calls as a function of the array size. And we have linearly increasing array size on the x-axis and linear running time in seconds on the y-axis. So what do we expect to see here if we plot this out? Does anybody have any thoughts? What kind of curve or plot should we expect? Waiting with bated breath. Bunch of people are typing. There we go. Okay, one idea is we might see multiple lines and slopes as we break cache levels. That's an interesting thought. Somebody wonders if it's going to be an exponential function. I would hope not if we've done a good job with our sorting routine. Between linear and quadratic. If we think from just a basic algorithms perspective, what do we expect to see here? We're just doing a basic comparison sort. Yeah, so for a large n, we'd expect it to asymptotically approach the complexity of sorting, so n log n, which a bunch of people point out. Another person points out that it should monotonically increase, which is a good point, and correlate with the asymptotic runtime, but it might be affected by other factors, like some people mentioned different levels of the cache. We might see, other interference like interrupts. Okay, so now let's look at what we actually see in this experiment. So we expect something that looks roughly like n log n growth, but this blue curve is what we actually observe. So the blue marks here are the actual measured running time of our benchmark at different sizes of n. And then the red and green are ideal linear and n log n curves that best fit those observations. So based on basic algorithmic analysis of sort, we'd expect something like the green curve. Like close to linear in this regime, but slowly bending upwards due to the log n term. But what we actually observe is this crazy oscillation up and down. The actual shape of these observations look almost nothing like the simple gentle upward slope of the green line. Maybe if we squint, the minimums, the bottoms of these troughs are growing in a simple n log n fashion. Maybe there's something going on there, but in between we see these wild upswings that are increasing in both frequency, so they're getting closer together, and magnitude. So the gap between the bottom of the trough and the top gets worse and worse. The peaks are getting bigger and closer together as n increases. All right, so what the hell is going on here? Does anybody have any ideas? page faults. It's an interesting thought. Anybody else? Actually, you should feel free to shout out too, I realize. If anybody wants to be daring and speak up and say something and explain why they're thinking that on Zoom, you're welcome to. Maybe not yet. Yeah, another idea is interference from OS scheduling would make us more likely to be interrupted. A few more ideas coming in. Some kind of memory or cache effects. Yeah, these are all good guesses. These are all complications of our real system that may make behavior not follow the simple the simple model that we use to derive analog n scaling, which is basically a model tracking the number of operations we perform. But it turns out in this particular case, this behavior is actually a consequence of a different feature of modern chips, which nobody mentioned so far, something called DVFS, or dynamic voltage and frequency scaling. And the basic idea of dynamic voltage and frequency scaling is it's a technique that can dynamically trade off power for performance by adjusting the clock frequency and supply voltage of transistors in the chip. So basically you can imagine your CPU, instead of running at a fixed clock frequency that needs a fixed voltage in order to be able to run correctly, the chip can dynamically reduce the frequency and after doing that, dial down the voltage and therefore decrease the power that it consumes. If the chip, for example, is running too hot, or if it's not so busy at a given point in time, we want to conserve energy and power. Like I said, when we reduce frequency, that gives us an opportunity to reduce voltage as well. It just turns out that the physics of our transistors is such that lower frequencies can run safely at lower voltage, or conversely, higher frequencies require higher voltage to run correctly. You can think of the converse of these reductions is what like Intel brands as turbo boost, which is the idea that maybe we have an opportunity to temporarily increase the frequency and voltage over the nominal rating of the chip, run even faster for short bursts of time if the chip's cool enough or hasn't been doing much recently. And the basic idea here is that since the end of Dennard scaling about 15 years ago, that we've talked about a number of times in this class, modern chips have been primarily limited by how much power they consume, how much energy they use to do a given operation, and how quickly they consume that energy. So how much power they use. And the idea with dynamic voltage and frequency scaling is that we say, instead of having a fixed power budget and taking that to dictate a fixed and conservative voltage and frequency that we could always safely run at, why don't instead we could make our system adapt? So we could run hard up to or even over some limit, and then track how hot our system's getting, how much energy it's consuming, what the power draw is relative to the physical limits of our system, and then back off as needed. So for example, your phone or laptop might give you a quick burst of speed, even higher than the nominal rated clock frequency, like the kind of default clock frequency of your CPUs when you touch the screen or load a web page or drag something with the mouse, and then slow down otherwise. You could even see different performance when you have your laptop or your phone outside in the sun versus in the shade or on a winter day or inside under air conditioning. And in fact, apropos of this class, Professor Lyserson hasn't had AC at home since the start of the semester. So sometimes his laptop will literally get too hot during lecture and slow down unless he puts ice packs on it because of exactly this effect. And the reason this matters, and the reason this can be such a high leverage thing is because the relationship of power to the voltage and frequency at which we're running our chip is given by this proportionality. So power is proportional to the dynamic capacitance, so basically like the amount of chip area and how often we're toggling different logic gates, which is a function of the chip and what we're doing. times the voltage squared times the clock frequency. So if you think about the effect of changing voltage and clock frequency together, they have a combined cubic effect on the amount of power. So even relatively small changes in voltage and frequency can have a huge effect on the amount of power that our system uses. So making our systems dynamically adaptive in this way is valuable for making them, run as fast as possible, but it can also wreak havoc on performance measurements because it makes the behavior of our system kind of context and environment dependent and dynamically adaptive. And it turns out in this particular case, the extremes that we saw in that graph were the result of a poor early implementation of a DVFS controller on I think an older generation Intel platform. Modern systems aren't generally quite this pathological, so the shape of the shape of this curve won't be quite so crazy and oscillatory over quite such a wide range. But this general behavior is still there in most computers you use, certainly in all your phones, tablets, laptops, and desktops. And it turns out that DVFS is just one of many examples of how hardware, compiler, and OS developers are working really hard to squeeze as much performance as possible out of our systems. But like DVFS, lots of these techniques, while they improve performance on average in lots of valuable ways, they can also make the systems more complex and dynamic and much harder to precisely control and measure. All right. So given complications like this, and more that we'll see today, as we'll see further today, this is just one of many potential issues. How do we even hope to reliably measure the performance of software? That's the subject for the rest of today's lecture. Instruction count. Good guesses. We'll get back to that in a bit. So overall, this is what we're going to touch on today. And I want to do that by talking about three different major issues. So first, we're going to talk a bit about what statistics and metrics to measure to quantify performance. Then we'll talk a bit about different tools we have, different tools and techniques for measuring the performance of software. And then finally, we'll talk about the concept of quiescing systems, or trying to bring under control some of these external sources of noise and variability, like dynamic voltage and frequency scaling, to give us more reliable, consistent platforms on which to measure performance. All right, so first, let's think about what we should be measuring and how we analyze it to make decisions about performance. So the first thing to note is that we have to decide what performance even means to us quantitatively. And more precisely, you can think of that as deciding what kind of summary statistic we care about optimizing. So in this class, in your projects, you focus almost entirely on running time. But as you take this knowledge out into the world, you're going to find that different metrics matter the most in different situations. So what you want to optimize is going to depend on your application context. So for example, if we're building some service, maybe we care about serving as many requests as possible on a fixed amount of server hardware. So we have a rack of computers, and we want to be able to serve as many requests or users as possible on that fixed amount of hardware. So in that case, a useful summary statistic would maybe be the arithmetic mean of the CPU utilization of our service as it's running. So that tell us something about the average amount of compute hardware that we use to fulfill requests. And we care about the arithmetic mean because the main metric we're interested in optimizing, or the main characteristic we're interested in optimizing, is the aggregate throughput, which is effectively summarized on a per request basis by the arithmetic mean. Another common example that you'll see if you work on internet services, for example, is wanting to hit some kind of latency bound. So, Google and others care a great deal about how fast their web pages respond to the average user, because among other reasons, they found that, I think Google's done experiments down to the level of like 10 milliseconds. Each time you double or cut in half the latency the responsiveness of your system, you significantly increase the number of queries that users will give it. People just prefer using snappy, responsive software, and they will use it more. Which, if you're someone like Google, is great for you because more searches mean more ad impressions and more revenue, et cetera. So maybe, for example, we want to make sure that most service requests are satisfied within 100 milliseconds. That's a good, it's not as fast as Google search, but it's a pretty good target for lots of web services, for example. So in that case, a good summary statistic might be taking the 90th or maybe even 99th percentile of the wall clock time, the end-to-end wall clock time for serving requests to users in different places. Another context, which you'll actually see in your last project, project 4 this semester, is building a game playing AI. In that context, you don't really care about, you don't directly care about runtime or latency or any of this at all. What you actually care about is the aggregate win rate that you're able to get. So a game playing AI isn't necessarily some specific algorithm. You get to both, choose the algorithm that you implement to make decisions and optimize that algorithm to run as fast as possible. So you can imagine that there's trade-offs between kind of the quality of guesses the algorithm's able to make and how deep it's able to search into the future. So maybe, sometimes it's better to do more approximate things, would be able to search a much bigger state space. Other times, maybe it's better to only be able to search a smaller state space, but be, thinking more deeply or doing more intelligent algorithmic stuff at each step. And overall, what you might really care about is like the mean win rate of your AI against other players. In other contexts, maybe you want to complete as many tasks as possible within a fixed time budget. So you might care about the maximum or mean wall clock time of individual tasks. It's really common in embedded or mobile systems to be able to worry about fitting into a fixed small memory budget. So you might care about optimizing your program based on its maximum memory use. If you're worried about something that can run all the time on a user's phone without making their phone hot or wearing out their battery really quickly, so if you're developing system features for iOS or Android or something, you probably care about performance, but you also care a lot about the mean or total energy use or CPU utilization of your code. If you're worried about the environmental impact of some process, maybe you can actually think in an end-to-end way about the carbon footprint. So think about the total amount of carbon used to solve, per task or to solve your task overall. And this is something that actually data center developers like Google and others actually literally do as part of their optimization. And then finally, in the real world, often you'll see what are called service level agreements, which often give some weighted combination of statistics on multiple different metrics, like 99th percentile latency, the maximum amount of downtime in a given window of time, and other features like that. All right. So now let's say for a second that we've chosen a metric that we want to optimize. So we've picked one of these summary statistics, of a particular metric of interest. That's what we care about. So once we've done that, we've defined what it means for one program to be better than another. So if we think back to our performance engineering loop, the core thing we're doing each time we test an optimization is taking two programs, A and B, and asking which one is faster or which one is better on the metric that we care about. But in the real world, our computer environments are noisy. So there's inherently going to be noise in our measurements of these two programs. We're never going to get perfectly precise and accurate measurements. So given that, what do you think we should do? What do you think are maybe some strategies that we could employ to make a decision about which program is better? Sorry, that poll is premature. That's coming up in a minute. Yeah, so some ideas people are coming up with are take the measurement multiple times and take the average. Could we delete that poll? I don't know how easy that is to do. There, thanks. We would run multiple different trials, time multiple times an average. Yeah, these are all getting at variants of the same idea. We could try to form some probabilistic bounds. We could fit a distribution. Yes, we could try to compute a confidence interval. Great. So in general, I would summarize the idea here, which multiple people are getting at, as we want to perform multiple evaluations. You know, the only hope we have for dealing with noise is to take multiple samples. So we're going to perform some n head-to-head comparisons between A and B, and then evaluate them statistically. What does that mean concretely? Well, one example you might have seen before in a social sciences setting or an experimental setting is evaluating p-values. So if, say, we perform a bunch of head-to-head tests, you know, run A, run B, run B, run A, do that a bunch of times, and we see A win over B more frequently than not. So p-value is all about saying, okay, if we consider the null hypothesis that we see A more frequently, but in fact, the true performance without the noise is that B would really beat A, the p-value tells us, you know, if B beats A, what's the probability that we'd observe A beating B as often as we did? So if the p-value is low, often in a social sciences setting, you might use p of 0.05, so a 5% probability that what we observe is actually the opposite. You know, B is actually better than A, even though we observe A beating B a certain number of times. You can dial the p-value, you know, your kind of threshold of confidence arbitrarily low. Regardless, with lots of noise, we're going to need lots of trials to be able to measure this very effectively. And there's other summary statistics. You can do t-tests and compute confidence intervals and other things that people also talked about. But in general, you can think about the comparisons that we're doing subject to noise as being like any other experimental science. So we need some amount of kind of rigor for thinking about how we actually evaluate our measurements. All right. So now let's think a bit more about measuring performance in a noisy system like this. So we're coming at this from a different angle now. And let's say we have a deterministic program. So it's going to, you know, we expect it to do the same thing each time we run it. We're not, you know, running something that's input dependent and, you know, running it with different inputs or something like that. So under ideal conditions with no noise, we'd expect the same result in the same runtime every time we tested it. And then we run it 100 times, but we know that our computer has some interfering background noise. So we don't expect to get exactly the same measurement every time. We're going to get some you know, noisy deviation from the true raw performance of the software. So what statistic do you think best represents the raw performance of the software in this case? And now is where the poll comes in. There we go. Do you think it's the mean, the median, the maximum, or the minimum? All right, no one's going for maximum. It's interesting. Or maybe somebody did for a second. Looks like we're getting a relatively even fight. Although median and minimum are pulling a bit ahead of mean. Seems like, yeah, some vacillation between different kinds of robust statistics. And the question doesn't heavily depend on the software. Actually, Phil, do you want to speak up for a second and expand on what you mean by that? If you're able to go on mic. Maybe not. There we go.
No. Hello?
So do you want? Yeah, go ahead.
Yeah. Oh, yeah. So maybe like if it's a random algorithm, maybe there's make some poor choices there.
Yeah, that's a great observation. So if it's a random algorithm, there's a key phrase I wrote on the slide here. You're getting at something actually really important, which I'll touch on in a second. So specifically here, we have a deterministic program that we expect to always do the same thing. But yes, absolutely. If it's a random program, that's a more complicated situation, which I'll come back to in a second. Some people think mean and median is the same. So it turns out that in this case, specifically in the context of a deterministic program, the answer is the minimum. So if you think about it, most noise in our systems is additive. You know, that there aren't magical ways our program could skip some instructions or some memory fetches. It always has some baseline amount of work it has to do. And most of the noise from taking interrupts from random packets coming over the network, page faults, other stuff, is just going to add to the runtime. And so it turns out that the minimum does a really good job at rejecting this noise. And the intuition is that, we expect most of the noise to be adding on to some fundamental cost of running our program. And this does get a bit more complex when there's randomness in the program itself, like Phil mentioned. And this actually comes up already in the programs you guys are running. So it turns out the Silk runtime system, which we'll learn more about on Thursday, uses randomized scheduling algorithms. And so even if you write what appears, what in the sequential, like what the serial projection of would be a completely deterministic program, so you don't have any randomness in your algorithm as you've declared it, just running it in parallel on the Silk runtime will introduce randomness. So in that context, something like the minimum might not be a very fair assessment, because the minimum is really going to be getting at the best case. And maybe, if we're randomizing, in the Silk case, we're randomizing the schedule by which tasks are distributed. Maybe there's one really tricky path through the program, or one really tricky schedule that happens to be significantly better than the average. And we don't necessarily want that as our summary statistic. I think it's an open question what the right answer is in the case of a non-deterministic program like that. But I think a pretty good model is, what a number of other people raised, that a different robust statistic like the median might better get at behavior in the case of a non-deterministic program. But the idea is somewhat similar. All right. If noise is dependent on a program, wouldn't a slower program that induces less noise still be considered better? That's a great and subtle question, and also gets at what it is that you care about in the environment in which you're running. Often it's a lot easier when you're doing the kind of low-level performance optimization that we do a lot of in this class. It's often a lot more practical to try to have a controlled running environment and just focus on the effects of how many instructions are executed, how quickly the processor can feed them through, how well you're using the memory system and stuff like that, and eliminate as much interference from background processes and other stuff that you don't control as possible. But if you care about, if you're Amazon building the virtual machine infrastructure or AWS, you probably actually do care a lot about, maybe average case performance or even worst case performance when you have lots of different unknown interfering processes running on top or interacting with each other. So yeah, it totally depends on what you're trying to optimize. Great thoughts. All right, so one last performance quantification puzzle to think about. So let's say we have two programs, A and B, and we run a bunch of different trials. So for example, maybe we have different inputs on each of these trials that we feed to each of the programs. Well, let's say our results look like this, like we have in the table here. So we have 4 trials. And in the first trial, program A takes, say, we'll call it 9 seconds, and program B takes 3 seconds. So the ratio of the runtimes, A over B is 3. This tells us that B is 3 times faster than A. We often call this ratio the speed up. It's the runtime of A over B is how many times faster B is than A. How many times B could run this task in the same amount of time it took A to run it once. In the second trial, we see that A takes 8, B takes 2. for a speed up of 4. In the third, we see the opposite. A is 10 times faster than B, so the speed up viewed from this perspective is 0.1. In the last case, we get a speed up of 5. So looking at this, so at the bottom here, we have the mean of each column. And if we think about the mean of this speed up term, the mean of the speed ups here is 3.03. So it'd be natural to say that B is on average about 3 times faster than A. Remember, each of these is saying how much faster is B than A, and then we're taking the average of all of those over different runs. So what do people think about this? Is this a good way to summarize the performance of B versus A? Nope. Good test taking skills? I'm raising a question, so the answer is probably not yes, it's trivial. Any ideas why? Does anybody want to maybe speak up for a second and propose a reason why? What might be issues here? So people are concerned about outliers. If we were only concerned about outliers, we could potentially take the median or something. But even if we wanted to know something, even if outliers weren't an issue, it turns out there's actually a different fundamental issue with this setup. So one observation that, giving us intuition into the fact that this is a problem is if you look at the mean of the runtimes, it's much closer than the mean of the ratios. Yeah, so Alex, I think, is hitting on something great here. So if we think about this a bit further, which is the example that Alex just raised, speed up is about the ratio of performance. And we can either think about the speed up of A over B or B over A. And those are just reciprocals of each other. And it certainly seems like if we take, so if we look at this is the speed up of A over B, this is the speed up of B over A. I realize it's a little bit confusing when I refer to it that way because that's the opposite of what how the ratio is labeled, but this is how much faster B is than A or how much faster A is than B. If you look at these individually, we see what we expect. They're reciprocals of each other. So B over A is just 1 over A over B. So 4 becomes a quarter, 3 becomes a third, etc. But, and if we think about that, if the average speed up from the perspective of B was about 3, we'd expect the reciprocal of that to be about 0.33. But if we average this new column, which is the speed up of A over B, we see it's 2.7. So we've got a paradox here. So the summary tells us, this kind of summary tells us that B is 3.03 times faster than A, and that A is 2.7 times faster than B. And clearly that makes no sense. But what's actually going on here? Well, it turns out that we're using the wrong summary statistic here. And specifically, the arithmetic mean is not a meaningful way to summarize ratios. So the arithmetic mean of A over B is not the inverse of the arithmetic mean of B over A. You can think of it as the arithmetic mean as an operation does not commute with taking ratios of the numbers in our set. Does anyone have any idea of what we might want to do instead? So yeah, Landon suggests, if anything, you need a geometric mean. I like where you're thinking. Do you want to expand on that at all?
Well, with the geometric mean, you, I think, would get the inverses property, but it still has the problem of not being like scaled by the actual runtimes. So the geometric means wouldn't match with, say, the arithmetic means necessarily, because if you had like really large numbers in one sample, then
yeah, the behavior of how like large outliers influence the distributions is going to be different. But yeah, absolutely. So it turns out that the general accepted practice here, the right summary statistic to use in this case, when we're dealing with ratios like speed up, or how much faster one program is than another, is the geometric mean. And the reason is exactly what Landon got to. So if you haven't seen this before, probably come up in one context or another in many of your classes, but If you're feeling rusty or don't know it by name, the geometric mean is a little bit different than the arithmetic mean that we're most used to. So where in the arithmetic mean, we take the sum of all of our measurements and divide by the number of measurements. In the geometric mean, we take the product of all the measurements, we multiply them all together, and then take the nth root. So for n measurements, we take the nth root of that. And intuitively or geometrically, you can think of this as saying, what is the like hypercube? What is the edge length of the hypercube that would have the same volume as the hypercuboid that has edge lengths given by all of our measurements. And the key property of the geometric mean is that it does commute with taking the reciprocal. So the geometric mean of A over B is the inverse or the reciprocal of the geometric mean of B over A. So if we look at that, if we use the geometric mean here on these two ratio columns, we see that the speed up of B over A is 1.57, and the speed up of from the perspective of A is 0.64. And those are indeed reciprocals of each other, which is what we want. So in general, when you're working with speed ups or things like that, like factors of improvement, things that boil down to ratios, you want to take a geometric mean, not an arithmetic mean. All right, so any questions on what we've covered so far? All right, I want to take a 2-minute breather, stretch break for a second, give everybody a second to catch their breath, including me, and then we'll come back and pick up where we left off. All right, got my shades down so the sun came out. Got some tea. Let's get back to it. Okay, so we were just talking about what statistics and metrics to measure, how we can quantify and analyze the performance of our programs from different perspectives. And now I want to talk a little bit about tools we have, different tools we can use to measure software performance. So there are a range of different useful tools and techniques for measuring performance. And you can roughly think about them each as falling into one of 3 broad categories. But first, you can measure the whole program, measure the metrics of interest for an entire program. And this is what you get by using, for example, the Unix time command, and also things like perfstat, cachegrind, or strace. Second, you can measure just part of the program. Maybe there's one critical piece that we care about, and there's different ways that we can isolate that piece and try to measure just that. And the one that we've seen most often, including in the code samples so far, is including timing calls directly in the program. So maybe we have a program that does a bunch of setup and other stuff, but we really want to know about the time through one critical piece. So we can include timing calls like Unix get time of day or clock get time, or the RDTSC instruction, which we'll see in a second, as ways of measuring time before and after that piece of the code. And then the last thing we can do, which is sort of a generalization of the idea of measuring a part of the program, is we can create a profile of the program that'll tell us some kind of breakdown of the amount of time or other other characteristics spent or observed throughout the entire program. So not a single summary of the whole thing, but kind of broken down by piece, like maybe by function, how much time we spend, how many CPU cycles we spend, how many cache misses we have, or whatever, in each function inside a whole program. And we'll show a few examples, and I think in the class we also have resources to use some other tools, but I'll show a few examples of profiling techniques or mechanisms. And a key thing which we'll come back to in a second is that you can compute this profiling, you can do finer grained profiling either using sampling or instrumentation. So you can think of instrumentation as basically the generalization of measuring part of the program by inserting calls to like a clock routine, and sampling is a different technique, which we'll come back to in a second. All right, so one of the simplest ways you can measure the execution time of a whole program is with the Unix time command. And it works something like this. Hopefully, this is probably something that at least those of you who are comfortable with command line have done on occasion, but the basic idea with time is if you have a program and you want to invoke your program with some arguments, so normally you would have called my program with say arg1 and arg2, but you want to know how long that takes to run, you prefix it with the time command. Usually you don't need to write the full path, but we're just being extra precise here. So you say time my program arg1, arg2, it's going to run your program just like normal. And at the end, it's going to print out a summary of how long it took. It's 3 different numbers, which you see here. So what does this actually mean? So we see these entries for real, user, and sys. And these are in units of time. So we see minutes and seconds. So what these actually mean, real is a measure of the wall clock time. This is basically the difference between the wall clock time when we started the program and when the program terminated. So in this case, this is like 3.5 seconds. User, by contrast, is the amount of processor time, active processor time, spent in user mode code. So this is code outside the kernel, but within your process. Then sys is the amount of time that the processor spent in the kernel servicing system calls for this process. So in this case, we actually see something kind of interesting. The total wall clock time to execute the process is 3.5 seconds. The amount of user time is only about 23 milliseconds, and the amount of system time is only about 5 milliseconds. So some of these is still less than 30 milliseconds, which is like 100 times less than the total wall clock time. What that probably means is either our system is really busy, and a lot of this end-to-end wall clock time is spent running other programs. So time slicing our processor between our program and other ones, or we spent a lot of time blocked on I/O. So maybe we put our program to sleep waiting for a result of a network request or something like that. So when it's asleep or blocked on I/O, it's not going to be either occupying the CPU in user mode or kernel mode. All right. So time is a really useful general tool, but often you want to measure the time taken by just part of your program. And a great way to doing that is just with the standard clock get time function available in modern C. So, and this is roughly what we saw in the example at the beginning of today's lecture, and I think you've used this probably already in homeworks and projects. So the basic idea is if we have a function that we want to measure, we could write some code like this. So we include the library that lets us call clock get time. We declare the structs that we're going to use for it to return its results to us. We get the time in monotonic mode right before we call our function. We run the function we're interested in, and we get the time at the end, and we can compute the difference. Really simple. So clock get time is really nice because it's both easy to use and it's pretty fast. So typically, clock get time in clock monotonic mode is, like I said, pretty fast, roughly 80 nanoseconds. So that's, on the order of dozens or, 100 or 200 CPU cycles, which is about 2 orders of magnitude faster than an ordinary system call. Clock get time actually is implemented by a system call under the covers, but modern kernels like modern versions of Linux have optimizations that let it follow a fast path where it actually gets serviced in user land most of the time. Clock get time also has some nice guarantees. So it's going to give us something, even if we have like dynamic voltage and frequency scaling like we saw before, it's generally going to do a pretty good job compensating for that and giving us something that relates to actual real world wall clock time. And it has some other properties that you might take for granted, but more detailed ways of measuring time don't necessarily. So for example, as the name clock monotonic implies, it never runs backwards. It turns out that that's a non-trivial thing to implement on a multi-core chip where different parts are speeding up and slowing down at different rates. So generally, clock get time is a great choice if you just want to measure the performance of a given piece of code. There are some caveats. Occasionally, it's not always fast. I think we've done a good job resolving some bugs that have come up in the past on the AWS machines that you guys use, and made sure that you should probably always be hitting the fast path here, although there have been some previous offerings in this class, I gather, where under certain conditions, clock get time was turning into a system call and becoming pathologically slow, which is not good, because then it's hundreds of times slower than this to run the measurement. All right. So speaking of measurement being somewhat expensive, we can think about different contexts in which we can apply this kind of technique, which come with different kinds of trade-offs. So first, we can generalize this approach of inserting measurement around a piece of code, and measuring how long that span of code takes. We can generalize this idea, do it at a bunch of different places in our program, and compute a profile of the time spent in different places. So we can insert instrumentation like this around each different piece of code that we're interested in. So for example, maybe we have these two functions, vecadd and vecscale, that we care a lot about. We could instrument inside them the amount of time they take to do their main work, and then report that time. And this would report the time taken for each invocation of each of these functions. And that's potentially useful because it tells us much more than a single summary statistic could. It breaks down the behavior of our program into lots of different data, how many times each of these is called, when it's called, and how long each call took. So that can be a lot more informative. But there can also be issues with heavy instrumentation for profiling. Can anyone think of some issues that might come up if we tried to do this? What might be a problem? Actually, just literally think of the code that we have here, where we have these little math helpers. Yeah, Lucy points out there's probably overhead to clock get time. So I said that this takes maybe 80 nanoseconds, I think. Doing like a vector add or a vector scale is like 1 or 2 instructions. That's a lot less than even the relatively fast time of clock get time. Another observation is maybe this prevents inlining. So we saw before in a previous lecture that helper routines like this often you want to inline to avoid the function call overhead. And clock get time is going to induce a function call, and no matter what. So it's very likely that that's going to prevent that optimization. So these are great thoughts. So in general, this instrumentation type approach is really useful, but there's a limit to how fine-grained our instrumentation can be. And broadly, you should watch out for what we often call the probe effect, where adding instrumentation alters the behavior of your program in unintended ways. So, one example here, maybe it prevents an inlining optimization that's really important. Another example here is it's just going to take what were previously some relatively cheap inner loop routines and maybe make them orders of magnitude more expensive. So the ratio of costs of different things is going to change a lot. And when you're dealing with parallel programs, you can often induce situations where changing and observing the code in different ways might alter how the code gets scheduled, for example, which can lead to different results. Okay, so another approach to profiling performance and figuring out where in our program it's spending the most time is what we call sampling. And the idea of a sampling profiler, actually, I want to make one quick comment here on program instrumentation. So I've shown this, everything we've done with instrumenting with timers so far, we've been doing manually by modifying our code, but there also exist tools that can do this automatically. So some compiler tools can transform your program at compile time to insert instrumentation like this, which can be useful because they can make sure they interact carefully with different optimizations or transformations, for example. And they also make the task easier. So the next way of profiling that we want to consider is sampling. Sampling is much more often done by automatic tools, although you can do it manually, which I'll explain in a second. And the basic idea of a sampling-based profile or a sampling profiler is that we're going to interrupt our program periodically at maybe regularly spaced or semi-random intervals. And then each time we interrupt it, we're just going to look at the contents of the stack to determine which functions are currently being executed. And if we do this a whole bunch of times, we're going to get statistics. We're basically randomly stopping the program and saying, you know, at each random point in time, what code is currently running. And if we do that a lot, it'll tell us the distribution or sort of the histogram of what code is running will tell us something about something proportional to how long we're spending, how long our program is spending in each of those routines or each of those parts of the code. And it turns out that this idea really is as simple as I said. You can actually implement it yourself using what you might call poor man's profiler by just running your program under GDB. You run it for a little while, you type Control-C, you hit BT to get a backtrace. It's going to tell you what the current call stack is, so you know what the stack of functions you're running is. Maybe you write that down. You resume it, wait a little while, hit Control-C again, repeat. And if you do that a whole bunch, you're basically implementing a sampling profiler by hand. Fortunately, that's kind of painful. Sometimes maybe you want to do that because you just have no idea what's going on. But more often, tools like gprof, perfrecord, gperf tools, et cetera, are things you want to use to automate this strategy. So they will basically run your program inside a harness that will interrupt it periodically and inspect what's happening and keep statistics on all this profiling information. So that can be a really useful, very low overhead way that tends to be at least somewhat less subject to the probe effect than instrumentation, and could tell you like how long is being spent in all the functions of your whole program. A key note, though, is that this approach is not accurate if it's not able to obtain enough samples. So in an effort to keep the probe effect at a minimum, gprof, for example, by default is only going to sample, I think, 100 times per second. And so you need, in order for that to give you a statistically meaningful picture of where your program is spending time, you probably need to be running your benchmark for a non-trivial number of seconds. Running a program that only takes a small fraction of a second under the default gprof settings may only wind up getting a few or a few dozen samples, which may not be enough to actually tell you very much. All right, so those are a few of the ways we can measure performance, and particular runtime at different scales, from the whole program to key parts that we care about to a full profile of the time spent in each function. But sometimes it's also useful to measure things other than just raw, wall clock runtime. Can anyone think of any, of some examples of things other than wall clock time that we might want to measure to understand performance? So what sorts of things could be useful surrogates for runtime of a program? Instruction count, number of instructions executed, yeah. Memory usage, a lot of people like instruction count, which is a great one. It's definitely a good proxy. Maybe one more idea coming in. Cache misses, depending on what you care about, absolutely. Yeah. These are all great ideas. Power consumed, good point. These are all great ideas. And the big picture is that, even if minimizing runtime is our overall goal, which it often is, depending on the situation or what we're trying to understand, it can be sometimes useful to measure some other surrogate metrics, which are related and can be key drivers of performance. So for example, if we're trying to, it could be useful to measure something about the amount of work we're doing. So that might be the number of instructions that are executed. We can often do that using hardware performance counters that our processors have, or potentially using instrumentation in the program. We can measure the number of processor cycles that happen. We'll talk about how to do that using the RDTSC x86 instruction in a second. We can also measure things about the number of memory accesses performed, the number of cache hits and cache misses, using either hardware counters or simulators like CacheGrind, which you've seen. Sometimes we expect to be bottlenecked, or maybe we're worried we might be bottlenecked on system calls. So it can be useful to count those using a tool like strace. And in parallel programs, often a useful surrogate statistic is something like span, which we can get at using Silkscale. Okay, so one of the surrogate measures I just mentioned are hardware performance counters. And it turns out that most modern hardware has a bunch of built-in instrumentation to count lots of different things going on inside the chip as our program runs. So these can keep track of how many instructions are executed, maybe how many instructions of different types are executed, how many different types of events happen, for example, like cache misses and cache hits, TLB misses, all that kind of stuff. And the great thing about hardware performance counters is that they're basically instrumentation that's built down into the hardware at a very low level and gets updated at the granularity of individual events and individual instructions executing through the real hardware. The downside of performance counters is that they're kind of hard to get access to. So fortunately, there are libraries and kernel modules and stuff that can help abstract this a bit. There's also constraints in the hardware in that you can usually only access about 4 or 5 of them, run about 4 or 5 of them at a time. So if you want to measure more than 4 or 5 things at a time, often you need to record and replay the same piece of code multiple times, which is the virtualization aspect that some of these tools provide. For your purposes, things like perfstat are actually a lot more useful than directly working with these libraries and kernel modules. They basically will give you a simple interface for running a program with some of the performance counters turned on. There's tons and tons of hardware counters in modern chips. Some are relatively straightforward, like number of clock cycles or instructions retired. Some of them are way more esoteric and really only make sense if you know deep details about the microarchitecture of that particular chip. But while this might seem like a wonderful thing to get to use, and they can be really powerful in giving you deep insight into what your real processor is doing running real code in the wild. Like I said, there's a few key issues. You can usually only use a few of them at a time. And many performance counters are non-deterministic, and we'll see an example of that in a second. They can be somewhat unpredictable in what exactly they give you and a little bit difficult to interpret. And unfortunately, I think these are the x86 hardware performance counters. Well, they're built into all modern x86 chips. I think they're unfortunately not accessible on the generation of AWS instances that we're currently using in the class. If one of the TAs working on infrastructure wants to correct me on that, feel free. But I believe, unfortunately, with the main assignments in this class, you don't have direct access to them. But they're a useful thing to know about when you go out into the world later. All right, so one example of a hardware counter that you can use is the x86 timestamp counter. So it turns out that x86 processors provide a special instruction called RDTSC, which is a mnemonic for read timestamp counter, which reads the timestamp counter. And the timestamp counter is a performance counter on the processor that tracks the exact number of clock cycles since the machine booted up. So it can give you really precise measurements of time. Remember, our clock period, we're running at like 3 gigahertz or something. So our clock period is a fraction of a nanosecond. RDTSC is also really fast. It's even faster than clock get time. So it takes only about 32 nanoseconds to run. And while you need to drop down to inline assembly like this to call this instruction on older compilers, on newer compilers like the one you're using in this class, it turns out there's a convenient built-in that you can call to directly use RDTSC. So this is really useful. And this is actually somewhat portable across different architectures too. So it's pretty easy to use, and it's really, really fine-grained, but it does come with some caveats. So it's not a panacea, so you need to be extra careful if you're trying to use this. So specifically, RDTSC, because it's a per core cycle counter, remember that different cores can go to sleep at different times, their voltage and frequency goes up and down at different rates. So RDTSC can give you different answers on different cores on the same machine at the same time. And because of that, because your processes can, your threads can migrate from one core to another over time, RDT, the timestamp counter can actually appear to run backwards. So if you take your start timer on one core, do some work, your process is interrupted, then starts running again on another core that hasn't run as many cycles since boot, and then you take the end time, you can actually wind up measuring an end time that appeared before your start time. So you need to be careful about issues like that. This is most useful at very fine granularity. Or if you can guarantee that your process is pegged to run on a specific core. RDTSC is also not a serializing instruction, so the compiler might reorder your code around it. So you have to be careful that your timer hasn't been reordered to a different location in your code than you thought. And importantly, like I said, not all cycles take the same amount of time. So if you're mostly concerned about wall clock time, different things like dynamic voltage and frequency scaling, turbo boost, which we talked about before, and the way that those things interact with different instructions you might be running. So it turns out that modern x86 chips have to reduce their frequency a little bit below their peak turbo level when running AVX instructions. If you're running vector instructions, but processor clock speed, maximum processor clock speed goes down a bit. So because of this, converting clock cycles to real wall clock seconds can be a little bit tricky. And most of the time, I think clock get time monotonic, which we talked about before, is probably going to be what you want. But this can be useful for very precise micro measurements of like the number of cycles elapsing in a fixed piece of code. All right, so another way you can measure different quantities related to performance is with simulators. So rather than trying to measure execution on our real machine, we observe and track different aspects of its execution on some kind of model of a machine that we can simulate. So one example of a performance simulator you've seen already in class is CacheGrid, which simulates a processor's caches to analyze memory behavior. And simulators are really nice because they can give you very accurate and repeatable performance numbers. You know, they're not usually running the whole real OS. They don't have interference from other processes. They can have simplified models of how the cache works that get at kind of the essence of, you know, maybe the locality of your program without secondary details of, you know, interference from other processes and stuff getting in the way. And in a sense, you know, for deterministic programs, simulators can give you a perfect answer with no noise from outside interference. You only need to run your program under simulation once if it's a deterministic execution. Simulators can be robust to the probe effect because the probing, in a sense, is built into the we're instrumenting the simulator to say, like, how many cycles execute or how many cache misses happen, rather than changing the program that we're compiling and executing. So it's, you know, it's often a lot easier to go in and collect fine-grained statistics without perturbing what we're measuring. But importantly, simulators often run a lot slower than real time. And they also, you know, the flip side of being kind of simplified, idealized machines is they don't always capture all the relevant performance phenomena. So for example, CacheGrid models a lot of the details of the caches in your target processor, but it doesn't model every single memory system feature. So it doesn't have a full model of how prefetching works, for example. Okay, so you can think of performance simulator metrics as one useful surrogate of real performance. And another powerful thing you can do with surrogates is try to estimate things about performance of our underlying machine from real data. So for example, if you imagine that we've measured the execution of 4 different programs to collect this data we have in the table here. So for each one, we have the time it took, the number of instructions it executed, and the number of cache misses that it had. And then say, we want to infer how long in wall clock time it takes on average to run an instruction and how long it takes to have a cache miss. So in this case, we might guess that the model of how our actual machine performs is going to be some simple linear function like this. So we can model runtime t as the sum of some time cost per instruction times plus some other time cost per cache miss. So I here is going to be the number of instructions we execute, and C is the number of cache misses. So with a simple linear model like this, you know, one natural but powerful thing we can do is run a least squares regression to estimate these parameters A and B. So we're computing the runtime coefficients, the coefficients that describe, that will predict runtime for each instruction executed and for each cache miss. So the units here are going to be in time. And that will tell us something about the average time each instruction took, or the average cost of adding one more instruction according to the measurements we took, and the average cost of adding the average time cost of adding one more cache miss. And if we do that regression, we see something like this in this case. So A is about 0.2 nanoseconds. So it looks like we can run about 5 instructions per nanosecond, which we think we're running on a 3 gigahertz processor and it's super scalar and out of order and can run a few instructions every cycle. That actually looks like a pretty reasonably calibrated number. And B is about 18 nanoseconds. So some number of tens of processor cycles if we miss in the cache, which is about the latency we expect, on average between like L3 and DRAM. So these numbers actually get at something fundamental about the underlying performance costs of instructions and cache misses on our real machine. And usefully in this case, we see that the R² coefficient of this this regression is 0.9997, which means we're actually getting a really good fit. As simple as it is, this model does a really good job explaining the data. 99.97% of the variation in the data is explained by the model. Cool. All right. I'll gloss over this really fast. There's some issues with this kind of modeling approach, which will be familiar for people who've done any statistics or machine learning. So we can add more detail to our model to accommodate more complicated effects by basically adding more basis functions. But you can run into trouble if you do that too much. If you over-parameterize your model too much, you may overfit. And so you don't know whether the quality of your fit's a function of doing a good job predicting or actually just overfitting to those specific points. A great technique you can use to see how predictive your model is split up your data, split it up at random, use a subset of the data, or you might call it training set in machine learning land, to fit the coefficients, and then use those coefficients, find out how well the model predicts the other half of the data. You find that the correlation coefficient on the second half of the data that you didn't use to fit the coefficients. So briefly, that's just a small taste of useful things to think about when using this kind of predictive model, but it can be a powerful technique for analysis. And last, I want to touch really briefly on the idea of quiescing systems, or ways that we can reduce variability. So usually we open with a thought experiment, which I'm actually going to quickly gloss over. But if you say you're an Olympic pistol coach, because MIT has a great pistol team, and there's 2 different shooters, you're considering which one you want to recruit to your team. Shooter A has a higher average score. They hit the bullseye and got some other shots landed towards the center of the target. Shooter B has a lower average score, but very tight clustering. So shooter A is more accurate, and shooter B is more precise. The intuition here is precision is actually way more useful. If you can reduce variability, you can often compensate for systematic and random measurement errors. So it's a lot more useful to have very precise measurements that you can use to compare different choices that you're making. So there's lots of sources of variability, and I want to wrap up by touching for just a second on a couple of these. And I'll leave the slides up, which allude to a few others. So we've already talked about some, interrupts from other processes, dynamic voltage and frequency scaling, and randomness and operating system process scheduling and other stuff. One that we haven't talked about is hyperthreading, which is a feature of lots of modern processors. And this matters because it creates even more opportunities for different processes or threads to interfere with each other, even at the granularity of a given time slice on a given processing core. And intuitively, you can think about what hyperthreading is doing as just this cartoon extension of a basic processor pipeline. So if you think of our basic architecture 101 5-stage processor pipeline, where we fetch, decode, pull out registers, execute, and write back instructions. If we have 2-way hyperthreading, which is what most Intel chips today have, what we're basically doing is saying we have the same execution pipeline. So we have the same set of ALUs, the same instruction decode logic, et cetera. But we're going to replicate the fetch units and the architectural registers. So we're going to be able to put two logical threads on the same physical core at the same time by having two instruction pointers fetching two separate streams of instructions. And this blue one, when it references, architectural register EAX, it's going to be pulled from the blue set of registers. And when the green one references EAX, it's going to be pulled from a disjoint set of registers. So we have separate sets of architectural state that those two processes see. Then we can basically fetch and execute, feed instructions to this pipeline from two separate threads at the same time without them interfering with each other. And it's great because we can get better utilization of our ALUs and everything else. So we can get higher aggregate performance out of our processor. But for performance predictability, it's problematic because we just introduced another source of dynamism, another way for things to interfere with each other. You can inspect the current hyperthreading configuration of your CPU on Linux by looking at the CPU info report. So if you learn how to read this, which is documented in the slide, you can see the processor IDs, logical processor IDs correspond to hyperthreads, but the socket and core IDs tell you about actual physical cores. So here we see two different logical processors, 5 and 13, that are actually mapped to the same physical core, core 5 of socket 0. So this is one of a number of examples of complication that can lead to interference in noise and measurement. And the general idea is that I want to leave you with, that if you leave all of these on, so say you have hyperthreading and dynamic voltage and frequency scaling and turbo boost, maybe you have other processes running in the background, you'll see tons of performance variability. So this is 100 different runs of the same program. And you see a kind of even distribution from running at the fastest speed to running 25% slower than the fastest speed. But just by changing a few things that we refer to as quiescing the system, so trying to reduce these sources of variability, so turning off turbo boost and hyperthreading, and configuring different aspects of OS scheduling and stuff to be more consistent, which we've generally done for you on the AWS nodes that you use, you can get way, way more consistent performance measurements. And even if this doesn't, even if you care about ultimately running in the noisy setting later, related to the pistol shooting metaphor, it's often a lot more useful to compare different program variants in this highly precise setting to be able to discriminate among them. And the ones that are consistently better here will often, will generally be consistently better in the noisier setting too. It's just easier to see. So we have some documentation here on a bunch of the useful stuff to do to quiesce a system. Like I mentioned, we've done most of this already on AWS for you, but it's a very important thing to know when benchmarking real code in the future. So I'm just going to leave it at that. And there's a few more references to other sources of noise that are kind of interesting in the last slide or two that I'll throw up online. But we'll leave it there for today. And thank you, everybody.
We have actually one more announcement, Jonathan.
Oh, we do? Okay. Sorry.
Okay, so Nick, can you make the announcement?
Yep. Hi, everybody. So if you were on Piazza, you might have noticed, and also if you did Homer 4, you might have noticed there were some problems with OpenSilk. So we released an updated version after talking to developers and figuring out those bugs. And you should be able to just update and upgrade your apt packages. I'll send the command in the lecture channel. But basically, the fixes are reducers no longer have a memory leak, or at least 99% of the memory leaks aren't there anymore. And also, some people were seeing problems with SelkSAN instrumentation when O3 was also on, which was a very weird case of LLVM converting a for loop into a very unusual form, and then SelkSAN not being able to instrument that converted for loop. But these are some of the bugs that have been fixed, and hopefully you'll be seeing better performance and less memory leaks from using reducers in OpenSilk in general. So please upgrade to that, because we've also updated the AWS run machines to use that version. So any programs compiled with older OpenSilk will not work. So I'll send the command out for that.
Great.
That's
And Professor Reagan Kelly and I will hang out for a little bit afterwards for anybody who wants to chat.
Thanks, Nick.
If you're going to stay to chat, please turn on your videos so we know who we're talking to.